In this video, we're continuing on from the previous videos where we got motion operating using the Control Techniques motion library. We'll continue working with the MCCT position axis interface and generate some indexing motion to make the final position loop tuning with. After this, we'll save the setup and generate an EtherCAT startup list. So just a quick reminder of the hardware that we've got going on. We've got a laptop, got Ethernet connection through to a Beckhoff IPC. This port's configured to be Ethernet based. This port is configured to be EtherCAT based. That port is then connected to the Drives EtherCAT interface, which in this case is an SI EtherCAT. If you've got a Digitax HD M753, that interface is built in, so it's not a separate module. But in this case, the module's then plugged into the M700, giving it EtherCAT capability. In terms of the motor setup, we've got a Control Techniques Dynamics servo motor with a pulley on the end to simulate load inertia. All of the useful information in this video is also backed up in detail by a comprehensive user guide, which is linked in the description, so there's no need to take notes. So, from the last video, we'd got to the point where we were able to see what was going on with the drive. We knew that our communications were working, we knew that our drive was enabled, and then we were able to jog, to cause that sort of hello world movement just to prove that we could control the axis. Okay, so for the purposes of this video, what we're actually going to do now is just to invoke some motion so that we can do the final position loop tuning. Now, built into this, we have several references. So you can see here are those. So we have absolute movement, relative movement, modulo movement. So if you've got a rotary application like a carousel or something like that, you've got the ability to direct motion within a certain modulo range. But what we've also got is auto index and auto reciprocate. Okay, now the difference between these two is auto index, it will just move by a set position in a single direction time after time after time, giving you something to tune to. Okay, auto reciprocate basically does the same thing, except for it's going to move by the same amount of distance forward and then move by the same amount of distance back. So pretty helpful kind of references, if you like, for tuning. So I'm going to choose auto reciprocate, click OK, and send that in. And then what have we got? So we need to set our distance, if you like, to something sensible. So I am going to say 2 revolutions, so 2000 units, because we set our scaling to be 1000 units per rev, so 2 revs, 2000 units. So that is okay. I'm not going to put any jerk in there just to make the profile a little more rough. And I think also what I'll do, just to make it a bit more severe, I'll change it so instead of taking a second to get to maximum speed, I'm going to set this down to 100, which will mean it'll, sorry, that's wrong, 10,000, there we go. So it has to get there 10 times as quick, so that should mean 100 milliseconds. So let's do that. Do the same for deceleration. There we go. Maybe we want to make that speed a little bit faster as well. So in fact, actually we'll make that 5,000 just to get it up there a bit. I might actually make these 5 times bigger as well, so it has to really work for it. And we'll see how this works out. We can just adjust it later if it's not right. So there we go. Let's just write those in. And at the moment our axis is on. And let's just see what this is going to do. So what we need to do now, so we've set up our motion. So we've said we want it to go back and forth by 2 revs. The maximum speed that it's going to reach is 5,000 units per second, and then we want to get there at 50,000 units per second acceleration and deceleration, so fairly rapid. Let's just turn on position reference. Oh, there we go. That's perfectly good enough for what we're trying to achieve. Excellent. So now that we've got our motion working, the idea being that this is sort of simulating what your real application sort of might do, we can now return to our performance tuning. I'm just going to close down, actually I might move this over there so you can kind of still see it working. We can return to our controls. So what I'm not going to do is engage any of this stuff. Okay, so these are the test controls that you might use, just for initial movement, so you can just get the axis working, just a little bit, just to make sure that the communications work and all that kind of stuff. We've already been through the process of tuning up the speed loop, and you can see it's doing a pretty good job because the axis itself seems to be following. It doesn't seem to be much in the way of overshoot. Okay, so what I'm going to do is enable the scope, and the one that we're kind of interested in, I suppose, really is making sure that our current loop, if I just stop it now, we are not going into current limit. Okay, and the one that we're interested in here is improving the AMC position error. Okay, so what this is saying is that we're peaking at around plus or minus 40 position units. Okay, now for this particular application, I know I've got a decent encoder on there. It's capable of about 2 to the power 21 encoder counts per rev. Okay, we're only running on 16-bit resolution from that, but I think we can kind of improve this a little bit further. So let's have a look at doing that. So if I start the scope again, remember we're looking at improving this red line. Okay, and what you've got down here is your P gain slider. So if I start to increase this, hopefully what we'll see is the position error start to change and reduce. Now I can hear that at the motor that it's becoming a little more severe. Could be that really the acceleration that I've got is not enough to really challenge the position loop that much. But normally what you'd find when you're tuning the position loop is actually moving this slider somewhere from the default. I put it back down to get really sloppy. There we go. Okay, so I've gone to set this down to a really low value, and you can see that the red line here has now got lots of error. There's lots of periods where it's non-zero. Okay, then as we move this slider over to the right, you'll find that all of that error should become smaller and smaller and smaller and smaller. Can you see? I stop. All this error now is little tiny spikes. Okay, and you can do this because we've got like a decent resolution encoder, but also because we tuned the speed loop up first to give us good performance. Okay, you can only ever tune your position loop up properly if you first tuned your speed loop. Okay, so the process is set up your ADS comms, then go in and set up your drive motor using Connect, then set up your realistic motion, connect your realistic load, the actual final application, and then come in at the end here and increase the position loop gain until you've got what you want from the application. Obviously, like any application, there will be a system stability limit, so you can't keep pushing on this and pushing on this. So my suggestion to you is push it as far as you need to achieve whatever following error that you actually need, and don't go any further than that, because what you're doing is you're giving yourself sort of system stability margin. The closer you take this to the end, the less margin you've got for stability. So you could end up in a situation under some dynamic loads where actually it'll just end up oscillating and you've pushed it too far. So the default of 25. So if I start this working again, I push this back down to 25, which is the default, gives okay performance. You know, it's not going to be the best that you'll have, but there's plenty of leeway to the system stability limit. Okay, if I push on this, so I've like doubled it, say by about here, you can see that now the area or the time that it's spending away from zero is considerably less. You know, we're only getting spikes during acceleration and deceleration, or starting and stopping effectively, which is about what you'd expect. Okay, every system's different. It's down to you to take a look and understand what's happened. So the second thing that's going on here is this value down here. Now we've automatically set the position loop speed gain clamp to 300 RPM to the normal default value. So normally what you would say is, if my axis is 3000 RPM axis, you would reserve 10% of that speed for the position loop speed correction. So what this means is, when we're applying speed to correct our position, this is the maximum speed that will be applied. And honestly, for most applications, you know, 99.9, most of the time you just leave this set to 10% and it'll function exactly as you want. It's only in literally the most brutally dynamic of applications that you ever want this particular parameter to be any higher. Okay, so for most of you it will be fine, and I would say probably for most of you, unless it's pretty demanding, probably the default position loop P gain will also be fine. I'm just showing it for completeness, because it could be that you've got a particularly tight tolerance on following error whilst your machine is working, in which case this is how to do it. And again, a bit like the response characteristic here, where you can adjust the overall range, you can do exactly the same thing here. So you can take it from, you know, 0 to 100 gain units to 0 to 200 gain units, and so on and so forth, depending on your application. Bearing in mind the absolute maximum that you can set this to is mostly determined by the resolution of the encoder that you've got and the particular load that you've got. So I'm just going to go back to my TwinCAT project and actually stop this. There we go, and turn off my axis. There we go. So my axis is now off, and we can go back to our Connect project. So I'm going to say that where we are now is pretty well tuned. One thing that you will notice is that now the axis has been disabled, the position loop controls are off, and this is simply because when a TwinCAT axis is disabled, it disables the AMC, and therefore the position loop gain, it's not actually doing anything because the AMC itself has been disabled. Okay, the values that we set are still there, so that's okay. So let's move to the last step. So we're at the end now. We've made our application work. In our case, we simulated it just by using the reciprocating position reference. And now we're going to save all of those parameters in the drive. We can then go and make a backup file, which I'd recommend you all do. So this is saying, I don't know, this is added year, month, day, time, and I'm going to say final setup. Save that. So now we've got a backup parameter file of everything that went on. And there we go. It's just brought up something so we can go and review those if we're interested. I think for the purpose of this video, I'm going to say we're not interested in that. And then finally, you can export a startup list. So this startup list basically is, you go to startuplist.xml and you'll find it in your Connect folder. So let me just click on here. So documents, control techniques, Connect, name of the project, devices. In our case, I haven't named the device, and startup lists. So that's actually this file here. Okay, so I'll just choose to save that. And then in another video, I'm going to show you how to consume this XML file and import it into the startup list for that particular axis. So I'm just going to save that, and I'll come back to that in a later video. So there we have it. The remaining videos in this series are either shorter how-to videos to how to tackle specific single tasks related to configuring your motion or configuring the axis, etc., or the detailed operation of the motion interfaces themselves.